Good day everyone. Today we will be discussing the role of histone modification in epigenetic regulation. To begin, let me introduce my group member. We have Dayang Jasmine Amira, Desi Elton Duni, Maria Freda Frederick, and Nurul Aisyah binti Romeo. Without further ado, let's get started. What is histone? Histone are proteins that contain unusual high concentration of amino acid, which are lysine and arginine. H2A, H2B, H3, and H4 are co-histone, whereas H1 and H5 are linker histone. Histone act as spool, which DNA will once again. From the diagram below, we can also observe the histone tail, which extend out and are subject to various post-translational modification. This histone modification play a crucial role in regulating gene expression by either loosening or tightening the interaction between DNA and histone. What is epigenetic? Epigenetic is a study of mechanisms that lead to changes in gene expression that can be passed from cell to cell and are reversible, but do not involve a change in the sequence of DNA, such as cancer and growing old. In simpler terms, epigenetic explains how gene can be turned on or off without changing the DNA itself. This is done through a mechanism like DNA methylation and histone modification. These changes help control cell function and can be influenced by factors such as environment, lifestyle, or disease. Because they are reversible, they also offer hope for treatment in conditions like cancer. How can histone relate with epigenetic? Histone play a critical role in epigenetic by influencing chromatin structure and gene expression through various modifications. These modifications, such as acetylation, methylation, and phosphorylation, affect how tightly DNA is wrapped around histone, thus altering the accessibility of gene for transcriptional activation or repression. This process is fundamental for regulating cellular processes like differentiation and DNA repair. In other words, when histone modification causes the chromatin to become more relaxed, it allows specific genes to be turned on and actively transcribed. On the other hand, tighter packaging caused by certain modification can silence genes. This regulation is essential for processes like cell specialization, response to environmental changes, and repairing damaged DNA, making histone modification a key component of epigenetic control. Acetylation. Histone acetylation, typically mediated by histone acetyltransferase (HATS), is often associated with gene activation. Acetylation neutralizes the positive charge on lysine residue in histone tail, weakening the interaction between histone and DNA, and promoting a more open chromatin structure which allows for easier access by transcription factor. Histone methylation. Histone methylation, mediated by histone methyltransferase (HMTS), can be either activating or repressive depending on the specific histone residue and the number of methyl groups. Certain methylation marks, like methylation of histone H3 at lysine 4, are often associated with active gene expression, while others, like methylation of histone H3 at lysine 9, are often associated with gene repression. Histone phosphorylation. Histone phosphorylation is post-translational modification where phosphate groups are added to histone protein. This process is catalyzed by kinase and reversed by phosphatase. Phosphorylation of histone primarily occurs on serine, threonine, and tyrosine residue, mainly within the N-terminal tail of histone protein. The modification can alter chromatin structure, influencing processes like gene expression, DNA damage repair, and chromosome condensation. In conclusion, histone modification are crucial epigenetic regulators that influence gene expression, chromatin structure, and cellular processes. That's all from us. Thank you.